how to implement this in code. Let us assume that we have a hash function h from the set of all possible objects S to the set of numbers from 0 to m-1. And let us denote by O and O prime objects from set S, and by V and V prime values from set big V. And let us have an array A, which consists of m lists, where m is the cardinality of the hash function, and those lists we'll call also chains. And those chains consist of pairs of objects O and values V. Now let us implement the first method, hasKey, which should return whether there is an entry in our table or in our map for the object O. First, we compute the value of hash function on the object O. We look at the corresponding cell in the array A and we take the list L from there. Then we go through this list, and when we go through it, we look at pairs O prime, V prime that are elements of this list. If for some pair O prime is the same as the object O for which we are looking, we return true, because it means that there is an entry in our map corresponding to the object O. If we don't find any corresponding pair in the list, we return false, because that means there is no such object and there is no key corresponding to this object in our map, because it only could be in the list corresponding to the cell with number h of O, and we didn't find it there. Next, let's implement method get, which should return the value corresponding to object O, if there is one, otherwise return some special value telling us that there is no entry corresponding to object O. Again, we start with computing value of hash function on object O, and looking at the cell number h of O in the array A, and take the list which is stored in that cell. Then we again go through all the pairs in that list L, pairs O prime, V prime, and if for some of the pairs O prime is the same as the object O for which we are looking, then we return the corresponding value V prime as the value corresponding to that object O. If we go through the whole list and we don't find corresponding pair, we return special value NA, which means that there is no value corresponding to object O in our map. Why is that? Because if there was some value, it has to be in the list corresponding to the cell number h of O, because that's the way we store our chains. And if we didn't find it there, then there is no entry corresponding to the object O. Now the last, most interesting method, set, which accepts two arguments, object O and the value V, which we need to set corresponding to this object. We need to either rewrite this value if there was already an entry corresponding to the object O with different value, or we need to create a new value in the map corresponding to the object O if it didn't happen to be in the map before. We again start with computing the hash function on the object O and looking at the corresponding cell in the array A, and we take the list which is stored there. Now we go through all the pairs P in that list L, and each pair P contains two fields. First field is P.O, which is the object of that pair, and P.V, which is the value of that pair. If for some pair we see that the object of that pair is the same as object O, for which we need to set the value V, then we just assign the value to the P.V, the new value. We rewrite the old value with the new value for that object O, and then we return, we exit from the function, because we've already done everything we need. If we go through the whole list and we don't find any pair corresponding to our object O, it means that there was no entry in our map corresponding to the object O previously, and it means that we need to add a new pair to our list. And we just append a new pair containing object O and value V to the list L corresponding to the cell number h of O. Now let's look at the asymptotics of the chaining scheme. The first lemma says that if C is the length of the longest chain in A, then the running time of all three methods is theta of C+1. First, if we look at the list corresponding to some object O, the list in the cell number h of O, then the length of this list can be C. This can be the longest list itself. And if object O is not in this list and we call some of the methods for this object, we will need to scan the full list. So we'll need to scan all C items in this list. Also, if C is 0, so that our map is empty, our array A is comprised of M empty lists, we still need constant time to check that. So that's why C+1 and not just C. Another lemma is talking about memory consumption. So let n be the number of different keys that we store in the map, and m is the cardinality of the hash function. Then the memory consumption is theta of n plus m. That is very easy to prove. First, we need to store n pairs of objects and corresponding values in the map. That's where we get theta of n. And we get additional theta of m to store the array of m lists. Although those lists can be empty, we'll still need to use some memory to store the pointers to the heads of those lists. And that's why memory consumption is theta of n plus m.